In the last class, we have introduced what is called quantum dynamics. And in that lecture, we have showed that the observable quantities, observable quantity or the output of a measurement are expectation value of an operator. Suppose if A is the action of measurement, then the output of the measurement is the expectation value of operator A. It can be represented as an angle bracket A, which is inner product psi A psi, if the norm of psi is unity, if it is normalized. Now this the expectation value of any operator has to evolve with time unless it is a conserved quantity. So in general, the expectation value of operator A must evolve with time unless it is conserved quantity. Okay, so then we can attribute the time evolution of the expectation value in different ways. And accordingly, we have three different pictures: a Schrodinger picture, Heisenberg picture, as well as interaction picture. Now, in this particular lecture, we are going to discuss about the Schrodinger picture. So, in the Schrodinger picture, the entire time evolution is attributed to the state of the system. The time evolution is attributed to state, and the operator is independent on time. So remember, the state of the system is actually an intrinsic thing, and the time evolution, we are referring to the state of the system in Schrodinger picture. So it has a certain philosophical implication. The philosophical implication of Schrodinger picture is there is an observer independent reality. So recall the action of observation is represented by operator. Okay, so in quantum mechanics, the action of measurement or observation is represented as an operator. Okay, so there is no time evolution for the action of measurement or for operators. The complete time evolution is for a state vector, which is an intrinsic quantity. Okay, so whether you measured or not, the state of the system are evolving continuously. Okay, so this implies that whether the observer performed, whether the observer performs the measurement or not, state of the system is always evolves with time. So this implies that philosophically we can say that there is observer independent reality. It is for the time evolution of the system, there is no requirement of the observer. Whether the observer is present or not, the system evolves with time. So the reality is independent on the observer. So that is what is called the Schrodinger picture, or the philosophical implication of the Schrodinger picture. Okay, so then we can move from the philosophy to the mathematical point of view. Okay, so the mathematically, what we have done is, what we have stated is the state, the psi is a function of time, whereas operator is not a function of time. Now, if the state is a function of time, then we can connect the state from some time t0 to the state to the time t. Now, the vector from at time t0 to t can be connected through some operator or through some linear operator, and that linear operator we can represent by symbol u. Okay, so the two vectors in the Hilbert space can be connected through the linear operator. Now, how we can represent the linear operator? So we can represent in this way: the state at time t can be written as u t0, the state at t0. Now u is a linear operator. Now we can check what would be the properties of this the linear operator u. So for that, first we can state that the norm of the state must be constant with time evolution. Must remain same in time evolution. Okay, so that means the inner product psi of t must be same as the inner product psi of t0 psi of t0. Now recall what is my norm. The norm of any vector psi is the square root of the inner product with itself. Okay, so if the norm is same, then the inner product must be the same. Now, how we can write psi of t? Psi of t, the ket psi of t is u acting on ket psi of t0. Now, what about the bra vector? So the bra psi of t is the bra vector psi of t0 u dagger. So u dagger t0 acting on the bra vector psi of t0 would give the psi of t, the bra psi of t. So this, therefore, the bra psi of t, I can write the bra psi of t0 u dagger t0 u t0 psi of t0 must be equal to psi of t0 psi of t0. Now, in order to satisfy this particular equation, the only possibility is this u dagger u must be identity. Okay, so left side is the inner product of u dagger u on the state psi of t0, and the right side is the inner product psi of t0 psi of t0. So in order to satisfy this equation, u dagger t0 u t0 must be identity. So this implies u dagger t0 u t0 must be identity operator. Okay, now if you look at this, we'll say that u must be unitary operator, but this is not a sufficient condition to state u is unitary, because this the u dagger u, that is we know that the operator usually do not commute. So u dagger u may not be equal to u dagger. So if u dagger u is identity, u dagger need not be identity. So in order to confirm U is a unitary operator, we should also have to prove the U dagger is also an identity operator. Okay, so usually this is enough, provided if the dimension of the vector space is finite. But in general, the dimension of vector space need not be finite. So in general, the dimension of vector space may be infinity. In general, dimension of vector space can be infinite. Therefore, in order to prove unitary property of U Tt0, we should also have to prove U Tt0, U dagger Tt0 is also identity. This is also required. So next we can see what would be this quantity, whether it is equal to identity or not. So for that, let us recall the definition of the time evolution operator. The time evolution operator U Tt0 is defined in this way. U to Tt0 acting on psi of T0 gives psi of T. Now let T be T0. Then what would be the left side? Left side become psi of T0 and right side become U T0 T0 psi of T0. So that means the U T0 T0 would be identity. Okay, so let this can be equation number 1, and this can be equation number 2, and let this be equation number 3. So again, we can have our equation number 1, which is psi of T. It is U T comma T0 psi of T0. Now if you replace by T1, then how we can write the psi of T1 equal U T1 comma T0 psi at T0. Okay, then now what would be the time evolution from psi of T1 to psi of T? So psi of T1 to psi of T. So that is psi of T we can write as U T comma T1 psi of T1. So remember U T0 connect psi of T0 to psi of T. Similarly, U T1 T0 connect the state at T0 to the state at T1. Now, how we can connect the state at T or the state at T1 to state at T? The state at T1 can be represented as psi of T1. That can be connected to psi of T as psi of T equal to U T1 times psi of T1. Now we have already written U T1. Psi of T1 can be written as U T1 comma T0 psi of t0. So the left side is psi of t, and the right side is u t1 u t1 t0 times psi of t0. Now the time evolution connecting the t0 to t can always be written as psi of t equal u t t0, the psi at t0. So this now by comparing these two equations, we can equate utt0 and utt1 ut1 t0. So that means u t0 can be written as u t1 u t1 t0. Okay, now here just replace t with t0, and what would be the left side? The left side will become u t0 comma t0 equal u t0 comma t1 u t1 comma t0. Okay, now what would be u t0 t0? Now u of t0 t0 is identity as per the equation number 3. So hence what you will get, this would be equal to identity. So we can write the right side first. So u at t0 comma t1, u at t1 comma t0 would be identity. Now this can also be written in another way. Now this also implies that, okay, so just change t0 with t and t1 with t0. How we can write this? So this can be rewritten as the u in the place of t0 will write t, in the place of t1 will write t0. So u t0 times u t0t would be identity operator. So this is our next equation. This equation can be written as question number 4. Okay. Now equation number 4 is this, and as well as we already proved that u dagger tt0 u tt0 is identity. Okay, so then multiply equation number 4 with u tt0 u dagger tt0 from the left side. So then you have to multiply this quantity from the left side. So this become u tt0 u dagger tt0. Then you have u tt0 u t0t. The right side would be identity times this quantity. It would be u tt0 u dagger tt0. Now what was the equation number for this equation? You just go back. Okay, that is equation number 2. Okay, now if you just look at equation number 2, from equation number 2 we can write this is nothing but identity. That is u dagger tt0 u tt0. So that would be identity. And hence the left side become u t comma t0 u t0 comma t equals u t comma t0 u dagger t comma t0. Okay. Now what would be this utt0 times ut0t according to equation number 4? That is also identity. So what will you get? So this is also an identity as per equation number 4. So finally what we have got is u tt0 u dagger tt0 would be identity. And that is our final equation. Equation number 5. So if you just look at equation number 4 and equation number 5, we have shown that u is a unitary operator. So combining equation number 4 and equation number 5, okay, sorry, equation number 2 and equation number 5 is this. So which is u dagger and u dagger u is identity, and this shows that u which is a time evolution operator is unitary. So next we can discuss how this unitary operator or the time evolution operator evolves with time. Okay, so we have seen that u tt0 can also be written as u t t1 u t1 t0. There is a time evolution from t0 to t can also be seen as two steps. There's a time evolution from t0 to t, sorry, t0 to t1, then the time evolution from t1 to t0. There is a time evolution from t to t0 can be viewed as t0 to t1 first, then t1 to t. So that is the meaning of this equation, and it is already proved by us earlier. That is here. With u t0 is u t1 u t1 t0. Okay. Now we are going to write t1 as t minus delta t, where delta t is infinitesimal time. And hence u t0 can be written as u t t minus delta t u t minus delta t to t0. Okay, now this is a finite transition in time t0 to t. Now this one is an infinitesimal transition. So this u t t minus delta t, we can call it is an infinitesimal unitary operator. Okay, now an infinitesimal unitary operator we can write as an expansion of a generator. that we have seen earlier, that if you have an infinitesimal unitary operator like u epsilon of g, then it can be written as 1 plus or minus I epsilon g. Okay, so a unitary operator or an infinitesimal unitary operator can be written in this way. Okay, so here G is called the generator of unitary operator. Now here we have a generator of infinitesimal unitary operator. Infinitesimal unitary operator. So this we have discussed as a tutorial for discussion of unitary operators. So therefore the infinitesimal unitary operator, which is u t comma t minus delta t, it is the time evolution from t minus delta to t, so it's a very small amount. So this can be written as identity operator minus I by h cross h times delta t. So here instead of g, I am representing as h. Here h is the generator. Okay. So then you can substitute this into our previous equation. Okay, so this is equation number 6, equation number 7, then 8, and substitute 8 in 7. This implies u t comma t0 when one identity minus I by h cross h times delta t times u t minus delta t t0. Then on right side we have two terms. One is u t minus delta t t0 minus I by h cross the h times u t minus delta t t0 times delta t. So take this first term to the left side, then what will get is u t comma t0 minus u t minus delta t t0 equal minus I by h cross h times u t minus delta t t0 times delta t. Take this delta t to the left side, then you have u t t0 minus u t minus delta t t0 all divided by delta t equal minus I by h cross h times u t minus delta t t0. Okay, now put limit delta t tends to 0 on both sides. So if you put the limit delta t tends to 0, the left side become the derivative of u with respect to time t equal minus I by h cross h u t comma t0. Okay, or we can write this as I h cross dou u by dou t equal h times u, it is. So this would be representing the differential equation satisfied by the time evolution operator u, and we can represent this by an equation number 9. Okay, so now we have the time evolution of the time evolution operator, the unitary operator satisfying or which controls the time evolution of the state has to evolve with the time according to equation number 9. Okay, so recall this h is called generator. Now in classical mechanics, the generator corresponding to the time evolution was the Hamiltonian, and that is nothing but energy. So similarly in quantum mechanics as well, the generator corresponding to time evolution is nothing but the Hamiltonian. And the Hamiltonian operator we can usually find once you know the classical Hamiltonian in the normal cases. And whereas if you have a non-classical system, for example spin, isospin, etc., then finding Hamiltonian would be slightly difficult. But the induction works so that we can have our previous experience to find the Hamiltonian of the system. Okay, so this generator of UTT0 is nothing but the Hamiltonian. Okay, now in equation number 9, just okay, if you have the equation number 9, we can write IH cross dou by dot T U TT0 equal H acting on UTT0. Okay, so in general, H is a function of time. H can be function of time. Now let us multiply equation 9 with psi of t0 from the right side. So if you multiply on the right side, what will you get? IH cross dou by dot T of UTT0 acting on psi of t0 gives H of t UTT0 psi at t0. What is the result of UTT0 acting on psi of t0? That is nothing but psi of t. So therefore we get IH cross dou by dot T of psi of t equal H of t psi of t. So this is the famous Schrodinger equation, or more correctly, the time dependent Schrodinger equation. And this is the equation of motion. In Schrodinger picture. Okay, so there's a complete evolution of the system. It can be covered in this particular equation. So once you know the initial state and the Hamiltonian, we can find the final state by solving this differential equation. And if you know the time, the state at any time t, then in general it is possible to find the expectation value at any time t, because the observable are independent on time in Schrodinger picture. Okay, so this is the famous equation. It can be put as equation number 10. Okay, so we already have a differential equation for unitary operator. We can have an integral equation as well. So equation number 9 gives IH cross or IH cross dou u t0 by dou t equal h of t u t0. So just integrate on both sides. So we can write integral of du dt0 from time t0 to t. So better put some integration variable as t prime. Then it will become minus I by h cross integral t0 to t h of t prime u t prime t0 dt prime. If you integrate du, we'll get u t prime t0 and the limit t0 to t equal minus I by h cross integral t0 to t h of t prime u t prime t0 dt prime. So put the limit. If you put the limit, you will get u t0 minus u t0 t would be identity. And this identity can be taken to the right side. So hence we can write this u t0 equal identity minus I by h cross integral t0 to t h of t prime is just a dummy index, dummy variable u t prime t0 dt prime. So this is the integral equation for the unitary operator. Okay, so it can be equation number 11. So we have an integral equation for unitary operator and the differential equation for the unitary operator. Now remember this equation number 11 is not the solution because on the right side again we have u. So this is not a solution. So this is an integral equation. Okay, but it is possible to find the approximate form of unitary operator by using equation number 11. Okay, so that's all about the Schrodinger picture, the first part of the Schrodinger picture. So we have some more discussion about Schrodinger picture in the next lecture. So the one thing is in Schrodinger picture, only the state evolves with time and operator is independent on time. So that is why we have, philosophically we can say that there is an observer independent reality in quantum mechanics using Schrodinger picture. Okay, so we have the evolution of state represented by mathematically this way. Evolution of state psi of t0 can be connected through an operator u, which is linear and as well as unitary, and the time evolution of that unitary operator is found to be by equation number 9, which is IH cross dou u by dou t is HU, and from which we can find the time evolution of the time equation of motion for the state vector, which is equation number 10, which is called the time independence Schrodinger equation. Okay, so that's all for now. In the next class, we can have some more discussion about the Schrodinger picture. Thanks for watching this video. We'll see you later.